The moment the port side hull cracked open, the progressive flooding geometry became an irreversible trap. The victim was the battleship Audacious. The stakes were a fully armed 23,000-ton dreadnought suddenly crippled in the open ocean. Water rushed through the jagged tear inflicted by a submerged contact mine. The ocean pressed against the steel plating with massive hydrostatic force. When the explosive payload detonated below the hull, it tore into the underwater structure around the port engine spaces. The shockwave fractured the internal structural framing. The immediate void filled instantly. The ship was heavily subdivided, relying on a complex network of steel walls to restrict flooding. The initial damage was severe but isolated to the port side. Had Audacious been fully at action stations, with watertight fittings already secured, the sea might have been contained more tightly around the initial wound. However, the true failure mode occurred deep within the ship architecture. The critical vulnerability lay not in one single wall, but in a chain of damaged and imperfect boundaries around the engineering spaces. Bulkheads, pipe glands, valves, hatches, and other fittings that let water keep finding routes inward. Once the seawater reached these central dividers, the pressure differential became immense. The flooded portside compartments pushed violently against the dry central and starboard sections. The central longitudinal bulkhead began to leak, and water bled from the port side into the central and starboard engine rooms. What began as leakage through compromised barriers grew into a spreading internal flood. The central and starboard engine rooms were slowly overwhelmed. This was not a sudden plunge to the seabed. It was a slow, mathematical death by progressive flooding. Each compartment lost meant a corresponding loss of buoyancy and, crucially, a loss of steam generation. The stokers and engineers fought to maintain boiler pressure, but as the cold Atlantic water swallowed the fires, the heart of the battleship stopped. Usable steam and electrical power failed. The massive propulsion shafts ceased turning. The ship lost all forward momentum. More importantly, as the auxiliary machinery failed, steering and hydraulic control were progressively disabled. The Dreadnought transformed from a self-directed warship into a flooded mass that could no longer hold a reliable course in the heavy ocean swells. Pumping capacity was no longer enough to keep pace with the flooding. Compartment by compartment, invading water displaced the air that kept the ship afloat. The internal geometry of the vessel worked against her survival. The longitudinal bulkheads, designed to protect the ship from broadside torpedo strikes, now trapped the incoming water on one side, forcing a severe and dangerous list. As the central barriers leaked, the water shifted unpredictably, pulling the massive gun platforms closer to the waterline. The focus on the bridge shifted entirely from saving the warship to saving the crew. Hundreds of officers and men were ordered to evacuate the doomed vessel. The discipline remained absolute under the shadow of the creeping list. The progressive flooding was slow enough to allow the organized transfer of the crew to nearby rescue vessels. Every single man aboard the battleship was safely removed before the final stage of the loss. Because the evacuation was methodical, the surface rescue vessels remained close by for hours. The surrounding ships precisely recorded the geographic coordinates of the vessel as she settled lower into the water. These surface observations preserved the loss area in official memory before the final sinking. The site could later be fixed by survey, but the original wartime position should be treated as an observed area rather than a perfect pin on the seabed. However, this same slow, agonizing process created a permanent forensic boundary. The exact mechanical failure of the watertight doors and internal bulkheads during those critical early hours remains hidden, because the volume of incoming water and the structural destruction that followed masked the original mine strike damage. The battleship was effectively a dead ship, slipping inexorably below the surface, but a parallel battle was already being fought to drag her to safety. The window for rescue was rapidly closing. Heavy ocean swells rolled in, and the powerless hull could only be moved by a massive application of outside mechanical force. The arrival of the immense passenger liner Olympic became the most dramatic part of a wider rescue effort. The massive ocean liner possessed the sheer engine horsepower theoretically necessary to drag the dying dreadnought towards shallow water. The rescuers passed heavy towing hawsers between the stricken warship and the towing ships. This initiated the harsh physics of brute force towing limits. The fundamental problem was not merely the combined weight of the two massive steel ships. The critical engineering failure point was dynamic tension. The dying battleship possessed absolutely no steam-powered steering to keep her heavy bow aligned with the direction of the tow. The rudder was entirely dead. The massive warship began to drift wildly off the intended course. Every heavy swell drove the Dreadnought off axis, turning the tow into a series of lateral shock loads. A heavy towing hawser can handle tremendous, steady pulling force along a straight axis. It cannot survive rapid, multi-directional shock loads delivered across an angle. As the passenger liner pulled forward, the flooded hull dragged sideways into the trough of the waves, steepening the line until the loading became violent and unpredictable. The hawsers parted repeatedly under the combined effect of the sea state, the ship's flooded weight, and the difficulty of keeping the damaged battleship under control. New lines were passed, including heavy wire hawsers, but the same pattern repeated. The rescue attempt was abandoned before dark. Once the vessel slipped completely below the surface, an entirely different kind of boundary was established over the site. A strict regime of official secrecy immediately locked away the true fate of the ship. The highest levels of command maintained the deliberate illusion that the Dreadnought remained an active combat vessel. This vast deception kept the exact resting location totally secure from enemy intelligence and opportunistic wartime salvage operations alike. Until late 1918, official confirmation remained suppressed under administrative silence. But the secret was never perfect. Passengers aboard Olympic had seen and photographed the disaster, and the wreck's later archaeological condition cannot be treated as pristine simply because the Admiralty withheld the news. However, the physical reality of the seabed imposed a harder barrier. At an average depth of 210 feet, under violent Atlantic weather and narrow windows of calm water, the wreck sits at the edge of practical access. Any work at the site must be specialized, carefully planned, and limited to technical diving or remote survey rather than ordinary human diving. Intrusive physical salvage would be practically, legally, and archaeologically hard to justify, and it would carry serious operational risk in such exposed weather. A sustained recovery would require heavy lift support to remain safely positioned over the wreck, but the exposed swell makes that kind of operation mechanically unrealistic. The site, therefore, had to be read through the water column by an entirely different mechanism. The deep ocean strips away all ambient light, turning the visual spectrum into an entirely useless tool for mapping massive targets. Conventional cameras require absolutely clear water and incredibly powerful artificial illumination, both of which are severely limited by the vast water column above. To characterize the immense footprint of the sunken vessel without any physical intrusion, marine archaeologists had to abandon standard optical systems entirely. They deployed a completely different methodology to penetrate the perpetual darkness. They utilized advanced multibeam bathymetry to systematically sweep the seabed. This technique relies exclusively on sound propagation rather than available light. By emitting dense fans of high-frequency acoustic beams again and again across the track line, surface survey vessels can effectively paint the deep sea floor using invisible sound waves. When these acoustic pulses travel through the cold water column and strike a hard, dense object like thick structural steel, they immediately bounce back toward the receiving surface sensor. The survey computers calculate the exact microsecond it takes for each individual echo to return to the receiver. Because the local speed of sound can be measured and corrected for temperature, salinity, and pressure, this timing measurement can be translated into a physical distance. Millions of these calculated distances are collected, processed, and aggregated into a highly dense, three-dimensional point cloud. This digital web of acoustic returns builds a highly accurate topographical map of the entire wreck site. The physical environment below might be completely dark and visually obscured, but the acoustic returns can still map exposed surfaces after careful correction for the water column and survey geometry. For the modern survey team, the breakthrough was not the act of scanning itself, but what the scan revealed. The multi-beam sweeps covered the debris footprint, exposing the inverted main hull, the broken forward area, and the scale of the warship lying across the sea bottom. The acoustic data clearly delineated the long, straight lines of the external hull plating and the sharp geometric angles of the primary armor belt. The sheer immense scale of the naval target was successfully translated into undeniable mathematical coordinates. It proved that a comprehensive, legally compliant site assessment could be conducted without violating the strict physical access boundaries. The survey vessels mowed the acoustic lawn over the site, running precise parallel track lines to ensure completely overlapping sensor coverage. This slow, methodical sweeping pattern guaranteed that no large structural features were accidentally missed in the darkness. The acoustic returns documented major exposed features of the wreck, while later visual and diving observations could confirm selected details where the structure lay open. By keeping the survey remote, the archaeologists preserved the forensic integrity of the site and extracted precise structural measurements without intrusive disturbance. The result was a coherent site-wide view of the exposed resting footprint. However, this remote acoustic methodology is bound by a severe physical limitation. Sound waves traveling through seawater absolutely cannot penetrate solid structural steel plates. The multibeam sonar can only map the very first hard surface it strikes from above or from the side. When an acoustic pulse hits a thick exterior hull plate, it bounces off immediately, leaving an acoustic shadow behind the barrier. That shadow prevents the remote imaging of deeply sealed internal bulkheads and leaves the enclosed engineering spaces unmapped wherever intact steel blocks the acoustic path. Yet where collapse has opened the underside of the inverted hull, exposed internal features can still be seen and surveyed. The remaining question is whether the original watertight boundaries can still be read with confidence. Despite these severe internal blind spots, the external scan was highly successful and highly revealing. The collected acoustic data formed a complete digital image, revealing a structural geometry that inverted the ship's massive weight against itself. The geometry of the seabed creates a permanent structural trap at a depth of 210 feet. A massive warship built to deflect plunging artillery shells and horizontal torpedo strikes possesses absolutely zero defense against its own inverted gravity. The remote survey confirmed the Dreadnought rests completely upside down on the ocean floor. This unnatural orientation fundamentally reversed the intended load-bearing architecture of the entire vessel. Components meant to work with a normal upright load path were now forced to carry weight in reverse, while the waterline belt and armored decks no longer sat in the relationship for which they were designed. Now they are pressed directly into the cold sand, bearing the total, crushing weight of the massive hull structure pressing down from above. The ship is effectively eating itself through sheer static pressure. The mechanism begins with the keel. It was designed to serve as the lowest structural foundation and the primary backbone of the warship. In this inverted position, that heavy spine now sits at the very highest point of the wreck, suspended far above the seabed. Gravity pulls this immensely heavy longitudinal mass relentlessly downward toward the ocean floor. The internal vertical bulkheads and the horizontal deck support columns were never designed or heavily armored to hold the weight of the massive keel suspended directly above them. Over decades of resting on the bottom, these internal support frames slowly buckled and snapped under the extreme unnatural load. The keel and lower hull structure collapsed over the internal spaces, pressing into the machinery areas as the wreck settled over time. The non-intrusive structural survey accurately confirmed this total internal collapse by strictly reading the exterior topography of the upturned hull. The collected data showed that while the outer armored edges of the hull remained relatively straight and intact, the central spine of the ship had deeply caved inward. The entire long line of the keel has sunk downward into the deep interior void, dragging the lower hull plating along with it in a massive structural depression. This clear external deformation proved exactly what happened deep inside the vessel without requiring any penetration. The internal decks and the critical engineering compartments are completely pancaked against one another. The crushing weight of the inverted hull effectively sealed the interior machinery spaces forever, turning the central block of the warship into a tightly compressed steel vault. The modern survey successfully documented this severe structural condition through sheer physical observation, achieving a critical understanding of the site without risking any physical disturbance to the heavy steel. This structural condition sets the proof limit for the central block. Technical divers or remote vehicles may observe exposed features, but they cannot reconstruct the original positions of every internal door, fitting, or engineering boundary from within the compressed wreck. The coherent evidence derived directly from the upside-down hull provides a complete structural explanation for the present condition of the heavy central block. It paints a perfect picture of slow gravitational destruction. However, the continuous structural lines of the main hull abruptly end long before reaching the forward tip of the vessel. The crushed main hull explains the resting state, but fails to account for the massive section completely missing from the bow. A slow, gravitational collapse cannot explain thousands of tons of heavy armored steel suddenly torn away from the main body. The initial mine strike alone possessed entirely insufficient chemical energy to sever the forward section so completely. The debris field immediately surrounding the main wreckage tells a completely different story of sudden, catastrophic destruction. The physical spread of the shattered steel proves the existence of a massive secondary event. The remote visual documentation recorded a vast scatter of detached components lying completely separated from the main hull. As the ship rolled over, or shortly afterward, a violent explosion occurred in the region of the forward A and B magazines. This blast created a destructive magazine overprint across the bow area, replacing the original layout with a secondary pattern of rupture. The massive blast wave shattered the heavy external framing, blowing the immense steel plates outward in every direction and severing the entire bow from the rest of the ship. The most compelling proof of this terminal explosion dynamic lies entirely off the main hull structure. The massive forward gun turrets, each designed to fire 13.5-inch armor-piercing shells, were discovered resting directly on the ocean floor a short distance from the primary wreckage. These incredibly heavy turrets are completely isolated from their circular armored housings. Their physical position on the sand provides clear visual documentation regarding the exact timing of the blast. Because the massive turret structures and barbettes lie displaced around the inverted bow area, their positions are consistent with a blast during the capsize or shortly after it. They support the sequence without making the debris field do more than it can prove. The detached geometry narrows the timing of the final destruction without requiring a single piece of steel to be recovered or disturbed. The incredible kinetic energy released by the detonating cordite was not confined to the immediate underwater environment. Historical accounts record that debris from the final explosion fell onto the nearby cruiser Liverpool, killing one petty officer. That fatal impact connects the violence seen on the seabed with the surface record without requiring the debris field alone to prove the exact range or trajectory of every fragment. While the detached heavy structures provide critical forensic proof regarding the final moments of the vessel, the surrounding sand dictates a strict operational boundary. The tremendous force of the blast did not consume all the available munitions. Large naval shells and other dangerous ordnance remained around the wreck, turning parts of the surrounding seabed into a hazard zone that restricts close approach, physical sampling, and disturbance by modern survey teams. The physical destruction was fully documented, leaving only the management of a highly volatile footprint. The resting place of the shattered Dreadnought remains permanently locked under an absolute dual authority of law and chemistry. The physical constraints that dictated the initial loss and subsequent surveys have fully evolved into strict administrative boundaries. The site is protected under Irish law as underwater cultural heritage because wrecks over 100 years old receive automatic protection. That legal status does not create a simple blanket ban on every possible licensed act, but it does make unauthorized diving, disturbance, artifact recovery, or salvage unlawful. Any physical work would require the relevant license and consent, and the default preservation principle is non-interference. The legal boundary is reinforced by the physical hazard still lying across the seabed. Some of that hazard may include degrading heavy artillery shells, buried torpedoes, and exposed cordite. Long exposure in seawater can leave old ordnance unpredictable, so the safe rule is simple: it must not be disturbed. Because of these compounding restrictions, the modern remote survey supplies the practical documentation needed to manage the sunken vessel. It mapped the visible footprint, identified terminal structural destruction, and characterized environmental and ordnance risks without lifting steel or publishing exact munition locations. The exposed physical condition of the warship is now established as a strong, non-intrusive baseline, not a perfect record of every hidden compartment. Regulatory bodies can compare future observations against that visible baseline, using acoustic maps as management records to understand what should remain in place and where the most sensitive areas appear to be. The maps support monitoring and preservation. They should not be overstated as an automatic enforcement system. The enduring condition of the massive wreck is protected, licensed only, and governed by non-disturbance. Remote evidence removes any ordinary scientific need for casual sampling, while the legal and ordnance risks make recovery an exceptional proposition rather than a routine option. The site remains mapped with precision, but its governing principle is restraint.